Hi everyone, this lesson is about equations of lines and planes. We start by describing equations of lines in two dimensions and look at the different ways that we can describe lines. We'll see that lines can be described using vectors. We will also talk about lines in 3D, and we'll talk about a new type of geometric object called a plane once we move into 3 dimensions. Shown here are two diagrams that represent lines and planes. These objects are objects that exist geometrically and objects that exist algebraically. We like to imagine lines as things you can draw on a piece of paper. Later, when we talk about planes, it's also something you can imagine drawing on a piece of paper, although I think it's harder to imagine. This is a preview slide of some key formulas that will come out of this lesson. You're going to see different ways you can describe lines, and they have similar sounding but very different names. Point, parallel, parametric, 2-point, point, normal, standard. Not very helpful names, I think, as when you're first learning about these different representations for lines. But you'll get the hang of it as you do homework. When we go into 3D, we'll see that some of these equations don't apply for lines, and they instead apply for other types of geometric objects, which are called planes. So a lot of this isn't going to make any sense because it's a preview. You can come back and look at those formulas after the lesson and use them as a type of summary slide. Up until this point, you've probably seen 2 or 3 different equations of lines. The most common form of a line is y equals mx plus b, where m is the slope of the line and b is the y-intercept of the line. You plug the x value in, get the y value out. A related form of that type of equation of a line is y minus y1 is equal to m times x minus x1. That is defined in the following way. So x1 and y1 are a particular point on the line that's given. M is the slope of the line. If you rearrange that, you get m, the slope, is equal to y minus y1 divided by x minus x1, which is delta y over delta x, which is your slope. And that's where that equation comes from. The last one here is an equation that not everyone would have seen, or at least if you've seen it, you may not have called it by this name. It's called standard form. It's ax plus by is equal to c. You can get this by rearranging y equals mx plus b. You can bring the mx to the other side, so you get negative mx plus y equals b. And then if you want, if m has a fraction in it, get rid of the fraction by multiplying every piece of that expression by the denominator, and then it's really going to look like ax plus by is equal to c. And it's that last one that we're going to use. You're not going to see y equals mx plus b used to describe lines anymore. You're not going to see the other one, the first one on that list. So we will eventually work our way towards standard form, but we're actually going to start with a completely new way to describe a line. We'll define the following quantity. A non-zero vector that points in the same direction of a particular line is called a direction vector for that line. I'm going to draw a line. Well, I've got to set my system up a little bit better. Don't rotate, please. Thank you. So I'm going to draw a line. I'll call it L. And lines extend forever in both directions. And sometimes when I draw a line, I'm not going to draw those arrows indicating extends forever in all directions, and that's just because I'm lazy. I don't want to always draw the arrows. But if I'm drawing a line, it is implied that those arrows are always there. The line doesn't stop, it goes forever. I'm going to draw one direction vector for the line. And this is the point, this is the origin, the point 0, 0. So here's my direction vector v for the line. I'm going to draw a second direction vector for the line. I'll call it u. Both of these vectors, and they both start at the origin. So this down here is the point 0, 0 if the line passes through the origin. Doesn't have to, but for the sake of drawing a nice picture, let's just pretend. What makes both of these things direction vectors is that they point literally in the same direction as that line. One of them is longer, one of them is shorter. Now we can also have a third direction vector, or a fourth, or a fifth. I'll draw one more though. We can have a direction vector go this way. I'll call it W. It's also pointing in the same direction as the line. A line itself does not have a forwards or backwards direction. So if it's a negative slope, let's say if W has or is in the negative direction of V, it's still a direction vector for that line. So again, all three of those vectors, U, V, and W, are direction vectors of the line L. How to find direction vectors? So we start with a line x plus y is equal to 2. This is just a concrete example, and I want the direction vector for that line. Now, what I'm going to do is not the way I want you to solve it, but I want to connect this topic to something that you're already familiar with. So I'm going to draw this line beginning with the x and y axis. Now, to draw this line, I want to put it into y equals mx plus b form, and I think this may be the last time that form is mentioned inside this course. So I have x plus y is equal to 2. I'm going to subtract x from both sides, so y is equal to negative x plus 2. That's a line that has a slope of negative 1. So m equals negative 1, and b equals 2. So I'll draw that line. Intercept of positive 2. I've got to draw some tick marks there, I guess. 1, 2, 4, 5. 2, 3, 4, 5. Maybe some negatives. Okay. So then I'll draw that line. We have when x is 0, y is 2. And then if x is 1, y is 1. If x is 2, y is 0. So that's our line. Okay, and it goes on forever in both directions. I want a direction vector that points in the same direction as that line. So I want this one, U, or this one, V. Those are both the direction vectors. I can construct them in the following way. I'm going to find a point on the line. Find a point on the line, and then I'm going to find a second point on the line. So find 2 points on the line. And this is the way I want you to solve it. I don't want you to draw a picture. I want you to solve it this way, algebraically. Find 2 points on the line. So for the first point, I'm going to let x equal something. So let's say let x equal 0. Then y equals negative 0 plus 2, which is 2. So the first point P is 0, 2. Now part 2, to get a second point in the line, I'm going to choose a different x value. So let's say 1. Let x equal 1. So we'll get then y equals negative 1 plus 2, which is 1. So our point Q is 1, 1. So there's our point Q. So I got 2 points in the line, and then recall from the first week that we can create the vector that is equivalent to the line that connects those 2 points. From P to Q, so I'll erase V. We're finding U equivalent to the a directed line segment that goes from the point P to the point Q. So 1 comma 1 minus 0 comma 2, which is 1 comma negative 1. So that is the vector that, and I drew a little bit too long, should fix it. That is the vector. So I'll just make it formal. So the vector u is equal to 1 comma negative 1. And it matches with our picture. And notice we didn't actually need the picture to solve the problem on the right-hand side, to solve it algebraically. The picture is just extra so that we can connect it to the old ideas. We can take this idea of a direction vector and use it to actually construct a new formula or new equation for any line. And that formula is given here. A line can be described by a point plus t multiplied by the direction vector v. So the point P is any point on the line. V is the direction vector for the line. T is a parameter that controls where we are on the line. Where we are on the line. And the last part, the part that causes the most confusion, is what is x of t? This is x comma y. It's an xy coordinate. It's a collection of all xy coordinates that's on that line. To get a particular xy coordinate on that line, you sub in a particular value of t. So it's all of them to get any one point on the line, choose a value of t. So I'll tell you how this works. You're starting at the point P. Then the direction vector tells you which way to rotate. So imagine a compass needle. It's spinning around. And it's going to stop spinning when it's aligned with the direction of the direction vector v. T tells you how many steps to take in that direction. So you're starting at a point P. I'll draw it. Here's the point P. Here's the direction vector v. And let's say it's let t equal 3. So we start at the point P. We go 1, 2, 3. 3 steps in that direction, and that'll give us one coordinate on that line. That's how we can construct the entire line by taking all t values, where t is any doesn't have to be an integer, it's any real number. Fractions, decimals, any number. We can write this in component form, and actually I'll do a little bit better than that. I'll say x comma y equals x comma y. The xy coordinate of all points on the line can be written from the point P, which has components P1, P2, plus t times the direction vector v, which has, or I should have said coordinates P1, P2, and direction vector v, which has components V1 and V2. Right, and just to test out this definition, let's write the point parallel form equation for each of the following lines. So part A is asking us for the line that connects the point P 3, 1 and Q 6, 0. So you know how to write this in the form of y equals mx plus b. You can get m delta y over delta x. B, rearrange from plugging in x and y, rearranging the formula for y equals mx plus b after you get m, and then there you have it. But we're not going to do that. We're going to construct this new formula. So we want this as our answer. X of t is equal to p plus t comma v. One misleading thing is that just because I called the point p doesn't mean I have to use capital P as my point. 3, 1. I could use 6, 0. Now I am going to use 3, 1 for my point, but I have complete freedom to choose the other point. So that's going to be 3, 1 plus t times the direction vector. I'm going to leave a blank for that. How do we get the direction vector? So we need to find direction vector v. We get it the same way we got the last one. V is equal to the vector that is equivalent to the directed line segment that connects P and Q. So we get that from Q minus P, 6, 0 minus 3, 1, which is 6 minus 3 is 3, 0 minus 1 is -1, so those are the components, 3, -1. That's our answer. That describes the line that connects those 2 points. If I let t equal 1, I get exactly that point. I get 3, 1 plus 3, -1, which is 6, 0. I get the second point. If I let t equal 0, I get the first point. And it's worth writing that down. So note, if t equals 0, we get p. If t equals 1, we get, I should say, we get x, y equals p. And if t equals 1, we get x, y equals q. So I just want you to confirm that. Verify this on your own. You can get other points on the line by subbing in other values for t. All right, here's another one. Let's construct the line that goes through the point 3, 1 with direction vector 5, 6. Well, this one's easy. We don't have to construct the direction vector. It's given to us, and we don't have to do anything for the point. That's given to us. So it's just 3, 1 plus, be careful with my writing, plus t times the direction vector v, 5, 6. That's it. We don't have to do anything else. That's the equation of the line that goes through that point and has that direction vector. Then the line through the origin. So origin, that's the point 0, 0 if we're in 2D. So inside this question, we will assume that we are in 2D with direction vector v 2I minus j. So this is equal to 2 times 1, 0 minus 0, 1, recalling from previous lessons what I and j mean. Our special unit vectors in the x direction and y direction respectively. Okay, so I'm going to multiply that 2 to the bracket and subtract, and we get 2, -1 as our direction vector v. We have our point P, 0, 0. So our line x of t is equal to P plus t times v, which is 0, 0 plus 2, -1 with a t in front, plus t times 2, -1. Make that a little bit neater. Okay, and we'll continue in the next video.